22 feet is rotating 11 rotations per minute counterclockwise. Considering a point on the rim of the rotating wheel, what is the angular speed and the linear speed? Which one would you like to do?
Let's do the angular speed. Or do we have to go to
No, I think that we can do either one.
what's the angular then?
Okay. Angular speed is a good one to start with because angular speed is directly related to the RPM. So anytime you know the rotations per minute, then you can figure out the angular velocity, right? So there's just different ways of measuring the same thing. So you know you have 11 revolutions per minute.
What do they want it in?
Radians per second.
2 pi rad.
2 pi rad
Over 1 rev.
over 1 rev.
And then go 1 minute over 6 seconds.
Okay, so revolutions cancel, minutes cancel, you're left with radians per second, and the numerical answer is 1.15?
Yeah.
Okay, then once you have that, we have the simple relationship between angular velocity, which is this, and linear velocity. What's the formula that relates those two? V equals r times w, or all to r times omega. So we just need to take this and multiply it by 22. Go ahead, what? Thank you. 25.34 feet per second. Okay? All right, any questions about that? Yeah, go ahead.
Here's how it went to radians.
Yep, that is a weird thing that formula works that has to do with the arc length formula. There's a way that you can do the algebra and show, but it just is always strange when you multiply radians and feet. I agree. Okay. All right. So here's a really important thing that I hope you understand. Okay. If you know the revolutions per minute, then you know the angular velocity. Those two measurements are the same thing, just using different units. Okay. If it says what's the angular velocity, you know the RPM. Awesome. If it says what's the RPM, you know the angular velocity. Awesome. Okay. And then you have that simple formula to get to the linear velocity. So okay, B. A wheel of radius 8 inches is rotating 15 degrees per second. So we need to figure out now 3 things. What is the linear speed, the angular speed in RPM, and the angular speed in radians per second? Sure. So 15 degrees. To change that into radians, I multiply by pi over 180.
Yeah. Oh, I didn't have it.
Oh, okay. So we get what, Joe? 0.26? Okay, so that gives you 0.26 radians. Okay, so if it's rotating at 0.26 radians per second, then we just found the angular velocity. And they tried to trick us by listing that as the last thing that you have to find. But that's actually the easiest person. Okay? All right, now we can work backwards once we know the angular velocity and we can figure out the RPM. Right? Okay, so I can take 0.26 radians per second and change that into revolutions per minute. Okay, by doing the opposite process of what we did here for part A. All right, so how do I change radians per second into revolutions per minute? Okay, 1 revolution is 2 pi radians, and this time since we're going the other way, the revolutions are going to be on the top and the radians are going to be on the bottom. And 60 seconds is 1 minute, same deal. So the radians cancel, the seconds cancel, and you have revolutions per minute. So multiply those out, divide by 2 pi. Don't forget to put the 2 pi in parentheses so that you divide by both 2 and 2.48. I really don't know if you can.
Really? I don't like regular.
Yeah, they're great. No, I don't either. I hate something with scratches. So.
Oh yeah, I like
speed, right? Okay? So velocity is what? 2.08, and that's going to be inches per second. So that, we're okay up till there, and then C gets a little bit scary. But you just know some things about our lovely planet. For example, what is the revolution per minute of Mother Earth? Or what revolution per minute? Colby? What's that? Oh. This 2.08 came from taking the angular velocity and multiplying it by the radius. Okay? Okay, so you are standing on the equator of the Earth, and the reason why they had to say the equator is because, as we talked about before, the Earth is not perfectly spherical. Okay, the bulge is in the middle, right? So the radius is going to be different. So you're standing on the equator of the Earth. No, you're standing on the equator. You're not in the middle of it. You're on the. So we do have a astoundingly high linear velocity, which we'll get to in a minute. Says, what is your linear and angular speed? What did you say, Logan? Right. You make 1 revolution per day. Okay. That's the thing that you should know about how the Earth works. Okay. So, yeah. So they don't really ask what. I mean, they don't say what units to give here. So you could say that your angular velocity, you could change this into 1 revolution is 2 pi radians. So you could technically say that your angular velocity is 2 pi radians per day. And you have correctly answered the problem. Right? Someone asked me on a day, what, like, how long days or something? There you go. You're going to have a lot of friends. Yeah, that's the angular one. Okay, right. And if you want to make it into maybe more nicer things, you could go per hour. No, what? For the. This one for B. Huh, interesting. Yeah, uber cray. So then we came up with 0.26 radians per hour, and you did that by dividing 2 pi by 24. Okay, so that is our angular velocity. So again, what do you do with that to change it into linear velocity? Multiply by the radius. So if you take the angular velocity times the radius, and this is going to be good because it's weird, but it's going to be miles per hour. Yeah, because you change that into hours, which is nice. So what do you come up with per month? 1,000.
I got 1,000. Yeah, I got 1,000.
Yeah,
I got 1,029.
So it's going to depend on your units, okay? But yes, we are cruising right now, over 1,000 miles per hour as we go around.
So when people call you slow, it's because
You're wrong. We're going over 1,000 miles per hour. To get there? Yeah. How long is it still going to get there?
I think it might be actually so fast because they don't.
Yeah. It's weird because they have that one, that island maybe Jupiter or something like that, and they launched that like 20% out of it.
There's also something to Jupiter, but on the speed.
I think Andrea Oswald told me that there's a website you can go to and it tells you all of the space probes that are on there.
Yeah.
They haven't launched in a long time.
There's one that's diving into the
Hi, Casey.
It's, hi, Casey. I hope you're having fun.
Say something rude. I hate all people. People are dumb. Okay, how's that? Especially slow ones and tall ones and short ones and fast ones. So just all of them. I just don't like any of them. Okay, D. An auto tire has a radius of 12 inches. An auto tire instead of a car tire? Why are they saying 12 inches instead of 1 foot? If you are driving 65 miles per hour, what is the angular speed in radians per second? And the angular speed in revolutions per minute. So 65 miles per hour is your what? Small tire? what is your linear velocity? 65 miles per hour. So you know that v equals 65 miles per hour. So there might be a temptation for you to say, oh, well, if I want to find the angular velocity, all I need to do is take that and divide it by 12. But we have a unit issue here, okay? Because the radius is in inches and our speed is in miles. So what conversion do you want to? Okay, so we're going to make 65 miles per hour into, well, we want to go actually radians per second. So let's go, we can do that in inches, but let's go into seconds also, okay? We'll get a more reasonable answer. So 1 mile is 5,280 feet, and 1 foot is 12 inches, and 1 hour is 3,600 seconds. So that will convert us into inches per second. Multiply across top, divide by the bottom, so what you get.
I got
1,144 inches per second.
That works really well.
You know, the kind of people that I really don't like is people whose first name and last name start with the same letter. That's just like driving me nuts. McKenna Miller. Ugh.
Casey really loves you though.
Oh, yeah, right.
That's
Didn't
really
think of that.
okay.
Yeah, true.
That was really
Okay, so now we have the linear velocity in inches per second, right? So what do we do to get the angular velocity? Divided by 12. Colby, do you get that? That now we're going to divide by 12. In the previous problem, we were multiplying by the radius to get the linear. Did we divide by the radius and see? No, we multiplied again because we had the linear velocity. So we took our angular velocity and multiplied it by the radius. Okay? So if you want the linear velocity, you multiply by the radius. If you want the angular velocity, you divide by the radius. So 95.3.
Yeah.
95 and a third. So what are our units here? Radians per second.
See, I was so confused. Like, I'm not going to really go on with that. I'm sorry.
Okay, I'm on it. I'll get through it.
Okay.
Thanks for your support, folks. Okay, so that's the angular speed in radians per second, and then we now need to get the angular speed in revolutions per minute. But I trust you guys can do that now by doing the same thing here. Yep, I'll give you a second. All right. So we're trying to change radians per second into revolutions per minute. We use the conversions that 2 pi radians is 1 revolution, and 60 seconds is 1 minute. Does that make sense? So I have 95 and 1/3 radians per second. That was our answer to angular velocity. We took the linear velocity and divided it by the radius to get the angular velocity. We're turning it into RPMs, revolutions per minute. So how do I do it? Okay, 60 seconds is 1 minute. Okay. No, multiplication it doesn't matter. Okay. Yeah, that's it. Just make sure, both of you, that when you're dividing by 2 pi, you have to divide by parentheses 2 pi. So divide by 2. All right, so what did you guys get for the RPMs here? 900 what, Ken?
910.37 revolutions per minute.
Okay, so RPMs is right there, angular velocity is right there. When you did 95.3 repeating times 60 divided by 2 pi?
You put minus by 50.
Okay, hey, did we also do number 4? Okay. 4 and 5, and was that it? Okay. Lee is running around the perimeter of a circular track at a rate of 10 feet per second. So what is that? Linear velocity. So we know that its linear velocity is 10 feet per second. Units are important. The track has a radius of 100 yards. You want to change the 10 feet?
Wait, what do they want the time?
Good question. It does not say, so we can choose. Well, I would like to say, I would prefer to say that 100 yards is 300 feet. Because that doesn't, then I have no doubt. Okay? Okay, so track has a radius of 300 feet. After 10 seconds, Lee turns and runs along a radial line to the center of the circle. Once he reaches the center, he turns and runs along a Once he reaches the center, he turns and runs along the radial line to his starting point on the perimeter. Assume Lee does not slow down when he makes these 2 turns. Okay, so the first thing we have to do is sketch a picture. Can you, in your head, see what they're doing to us here? What false situation they have created? What does his route look like? It's a wedge, right. They're making us do a problem that involves a wedge of a circle. So he starts here. He goes for how many seconds? 10 seconds. So how far does he run? So how far does he run? 100 feet. If the radius, just for funny, if the radius of the circle is 300, what's the circumference? 600 pi, which is what? I'm just trying to see how big of
1,884.
big track. So 1,800 feet.
Yeah, sorry, yeah. It was like more like 19.
Like 1,900. So if he's going to go 100 feet, he's not going very far, right? On the track. Okay. So he's only going to get to here, and then he turns for some strange reason, goes to the center, and then comes back out. I don't think so. Yep. Okay, so here's where he starts, here's where he turns, and here's the center. That's my... more patience than for that. I thought it was just an excuse to make a busy reason than busy. No, it's like that's basically what is the Forever Tomorrow or whatever where the guy kept dying and then he goes into what was that? No, that was the one on the train. Is that one? Yeah, that was right. No, the one where you had to fight the people.
The train one, I know.
Yeah, that was like basically just a video game. You get a little farther and then die and then restart. Okay, how far has Lee traveled once he returns to his starting position? Easy question. How far does he run along the track? We already figured this out if you were listening. Okay, after 10 seconds, he's going 10 feet per second for 10 seconds. 100 feet. Okay, that's the people here. Don't get all, you get so quick. Wow, coming out right away.
Don't make that face. I'm not in a good mood now. Can you hear that? You just ruined my day.
700 feet, good. Because 100 here, 300 in the middle, 300 back out. So he went a total of 700 feet. Okay. How much time will it elapse? 70 seconds, good, because he's traveling at a rate of 10 feet per second. He goes a distance of 700 feet. So 700 divided by 10 is 70 seconds. Okay?
I have a question. So why is it only 700
Yeah, so he.
But like, where do you end and start, like, where do you
Okay,
end?
so he starts here, right?
Yeah, I got this 100,
Okay, 100.
400, 700, but then another 100 to go up.
No, because this is his starting point, so once he gets back to there, he's done. Okay. Okay, D, find the area of the pie-shaped section enclosed by lead path. Okay, so how do you want to do that? Okay, yeah, that's awesome, because if we do S equals R theta, we know what the arc length is, right? And we know what the radius is. So this will allow us to figure out very quickly what this angle is, all right? And then once we know that angle, we can use what we did in chapter 15 to figure out what fraction it is of the entire circle and multiply by that. Does that make sense? Does our problem solving strategy make sense?
Yes.
Okay, so 100 feet equals 300 feet times theta. And again, this is super, super weird. What?
It's going to go to radius.
It's going to go to radius.
Which is, yeah.
So when you divide 100 by 300, then you end up with 1/3 of the radius. Awesome. And then we have a formula for the area of a wedge, which is 1/2 r. Is there a square in there?
No.
R theta. Ooh, that's my rap name. R theta. That just happened. I've been waiting. You don't understand. I've been waiting for that my whole life.
No, you haven't.
Yeah, I have. Because you see all these guys, and you're like, okay, his name's Thomas. What? Where does that even? His name is Thomas. That we're the guy, Thomas. So how come I can't have just a name like that?
So R theta.
R theta.
R theta now.
No, it's a rap name. It's like Hannah Montana and Miley Cyrus. Okay? Yeah, Mr. R theta to you. Double what? I'm gonna. No. No.
Yeah, instead of monster and golf,
Hashtag R theta.
Yeah, I go home and tweet that. Have that aspect.
Okay, meanwhile, while you guys are goofing around with all your stupid rap stuff, I'm solving the problem.
Really? Because I already did it.
0.5 times the radius, which is 300, times 1/3, which is the angle, tells you that that is 50 square feet. Okay? All right, last one. So we are going to, you heard here first. Okay? We're going to see the Ferris wheel situations again and again and again. This is a recurring problem in this class. This is our introduction to it. Okay? So focus up a little bit, because it's probably going to come up on some sort of a quiz or test or whatever at some point in your life, something having to do with it. All right, so it says John has been hired to design an exciting carnival ride. Tiff, the carnival owner, has decided to create the world's greatest Ferris wheel. Tiff isn't into math, she simply has a vision and has told John these constraints on her dream. 1. The wheel should rotate clockwise with an angular speed of 12 counterclockwise, sorry, with an angular speed of students knock me down every day. They're all over me, everything I'm saying. The linear speed of a rider should be 200 miles. Okay, the linear speed of a rider should be 200 miles per hour, and the lowest point on the ride should be 4 feet above the level ground. So you basically have been hired as a consultant to TIP, so that you can, figure out what the dimensions are, what kind of things you need to put together to make this Ferris wheel a reality. Okay. So the first obvious question that you would come up with is, what would you need the radius of the Ferris wheel to be in order to figure out all of this stuff? Okay. All right. So what's the formula that we have that has radius in it that we can use to do that? Okay, we could use the area formula that we did in the last thing, but she hasn't told us anything about the area, okay? What do you say? V equals RW, okay? Do we know the velocity of the wheel? Yes, 200 miles per hour, okay? Do we know the angular velocity? Okay, good. So we can use this information to figure out what the,
How do you do this conversion-wise? Like,
yeah, so we got some work to do here before we make this
I literally don't know what conversion
happen.
is.
Okay, well, we just need the units to match. Okay? So we've got hours right here, we've got minutes, so that's a bad thing. Okay, so you want to change the 200 miles per hour into minutes. All right, so that means that I need to go 1 hour is 60 minutes. I have to divide that by 200. Anything else that we need to change? There is one more thing we need to change. What did you say? Yeah, we need to change good revolutions in the radians. And then once we have changed revolutions in the radians and hours in the minutes, then we're okay. And then we're going to end up with, yeah. So 1 revolution is 2 pi radian. Okay, so over here, if I go 200 divided by 60, 3.3 repeating. So that means that we're going 3 point, wait a minute. 200 miles per hour, is that right? Oh, okay, yeah, sorry, I just got that. Yeah, I was confused why we got a smaller, answer, but I'm back now. Alright, so that's going to equal the radius times, these revolutions will cancel, 24 pi radians per minute, okay? So, when we do the math here, when we divide to get the radius, here is the $1,000,000 question. What will the unit of our answer be?
Miles.
Nope. Nope, miles. Okay, because the minutes are going to cancel, okay, and the radians magically turn into, go away, and so what we're left with is miles. So that's kind of an awkward unit for us, so we can convert that in a little bit.
I got .044.
You got what? Say that one more time. .044. Okay, so .044 miles. Let's get that at least into feet. 233.4 feet. Okay? Questions on how we did that? There was a lot going on. That's the radius of the Ferris wheel, yeah? We okay? Everybody follow that? So we just had a little bit of a unit conversion there, and I think that's why this chapter is so confusing, is because the unit conversions along with the formulas make it a little messy. Okay?
What did you say? What was your rap?
Don't even go there.
All
All right. Once the wheel is built, John suggests that Tiffany should take the first ride. Okay? The wheel starts turning when Tiff is at location P, which makes an angle theta with the horizontal as pictured. It takes her 1.3 seconds to reach the top of the ride. So it takes her 1.3 seconds to get to here. We want to use that to find that angle right there. What's this at? How in the world do we do that? Hold on a second. The wheel section where this is at location P, which makes the angle theta with the horizontal. Oh, okay. Well, I guess we know that this is 90. We can find this whole angle and then subtract theta from this. Okay. Yeah, keep following. What? This is going to be 90 because this is horizontal instead of this. So we're going to know that this is 90. We can use the fact that she traveled 1.3 seconds to find this angle and then subtract 90. Okay. Wait until we get to part 3. Yeah. Okay. Okay. So how do we find this entire angle right here? You know what? ignore that for right now. So we want to find this entire angle right here that she made from where she started to the top of the right. What's that? We could do it by finding the circumference.
If there are any sophomores or juniors out there who are interested in taking classes at the beauty school, there is a blue bell there, it is 404, so you representatives from that school, and you can go there now. Any sophomores interested in beauty school.
Okay, so we need a formula that involves this angle. What is that formula? S equals R theta, yeah. Okay? I'm going to trademark that, so every time somebody says that in a math class, I get royalties. Okay, so S equals R theta. Do we know, what do we know? We know the radius. So the radius we figured out was 233.4 feet. We're trying to find that angle, so we don't know that. We don't know the arc length either, but can we figure it out? Yes. What do we know we got going right? Steve, what if we know the angular velocity, yes? So we can find the angular velocity. And we also know the linear, I guess this is better. We know the linear velocity, right? The linear velocity is 200 miles per hour. So how can I use the linear velocity to find the arc length if we know that this takes 1.3 seconds? There's all kinds of weird fun things that we can do, but I think the easiest is if you think back to the guys just now running around the track, we know that distance equals rate times time, right?
Yeah.
So that arc length is the distance that we're trying to find. Okay? We know the rate is 200 miles per hour. And we know the time is 1.3 seconds. So if we multiply those things together, then we will get the distance, which in this case is an arc. Does that make sense, kind of? That's a little bit messy, but I think that's the easiest way to make this work. Right. Yeah. So yeah. Okay, we got to do some changing here, right? Yeah, because our radius is in feet, so we have to change the miles into feet. Okay, so 1. Yep. We're also going to have to change the hours into seconds so that when we multiply by 1.3, the time units cancel. So this is a little bit wacky. Yep, 1 hour is 3,600 seconds. And then once we get that answer, to find the distance that they traveled, multiply by 1.3 seconds. So if we did this right, the hours cancel, the miles cancel, the seconds cancel, and we're left with just feet. Okay? So that was a lot to figure out the arc length, but just times it by 150. Okay. Yep. Okay. So the arc length is 381.3 receiving feet. Okay. So we have the radius, we have the arc length. So how do we use that to figure out what the angle is? Okay, good. So 381.3 receiving divided by 233.4. Magnitude of feet turns into radians. Okay. One more time. Radians. Okay. So that was all a little bit crazy, but what we just figured out is this whole angle right there is 1.63 radians. Okay. How do we figure out what just this little tiny guy right there is? 90 is degrees, and our answer is in radians. Okay, good. So how many radians is 90 degrees? No, half a pi. Okay, half a pi. So if you take this answer right here, 1.63 radians minus pi over 2 radians, then that will give you that tiny little width. Okay. this one, the angle theta is 0.05. Okay, then the last one, no, we're not going to get anything new today. Last one, for engineering causing tip seat to fly off after 6 seconds. Describe where tip is located and angle description. The instant she becomes a human missile. Okay? Boom! Straight down. Okay, how do you know she goes around at least once? What's that? Hold on, I just want 12 revolutions per minute. Okay, so she's going to go around more than once. Yeah, she gets, yeah, that's a good point. She gets to the top at 1.3, then she's going to get all the way around. Okay. Right, okay, so good prediction is 90 degrees every second. 1, 2, 1, 2, 3, 4, 5, 6. That could be somewhere over here. So yeah, she might end up going straight into the concrete. Do you think she's going to go off this way? Okay.
Well, she'll go straight.
Go this way? She's going there. Okay.
No, this time here. Where does she initially fly off?
That's what we're trying to figure out. And then we know she'll make a straight tangent line from there. We just want to know if she's just going to smash right into the pavement or if she's going to launch from there.
Or she's going to be at the very bottom. She's going to drop off.
Okay, well let's figure it out. And to figure that out, we just have to do the same thing we did before. We know the time, right? And we know her speed in miles per hour. So if we go back to this stuff over here, we can use the same thing we did before to figure out the arc length that she goes through, right? And then if we take that and divide it by the radius, then again we'll figure out what angle she has traveled. Okay? So what is her speed? What is her speed? She's going 200 miles per hour, right? So we have her rate in her time in seconds. So I know we kind of did this before, so this is a little bit redundant, but how do I change that into miles per second? And I need to go feet also, don't I? Because the radius is in feet. We're doing the exact same thing we did before. So 1 hour is 3,600 seconds, and 1 mile is 5,280. 293.3 routine. Yeah, we had that already, didn't we? Okay, so that is her linear speed. So to figure out how far she traveled in those 6 seconds, what do I do with that answer? Multiply it by 6. So her distance is equal to her velocity times her time, which is 293.3 repeating times 6. And so that works out to be 1,460 feet. So she's going to travel a total of 1,760 feet in that exciting last 6 seconds of her life. Okay? How do we figure out what the angle is then? Yeah, we're going to do the arc length thing. F equals r theta. So the arc length is this. 1,760. The radius is, I don't remember. 200 what? 233.4. So you divide those and you magically get an angular radian. 7.54 radians. Okay, which really means nothing to us because we were raised in degrees. So can we change that into degrees so we get a sense of how many revolutions we have? So 7.54 times 180 divided by 432.0. So we'll go 432 degrees. All right. So if I subtract 360 from that, that leaves me with 72 degrees. Okay. Yep. So as you said, she's gone around once, so she's made it all the way once around. Things looking pretty good. She's thinking, wow, this is really fun ride. And then 72 degrees later, right about here, maybe somewhere, she goes into